tree diagrams, let's look at a specific problem. This is actually a problem on page 342. You don't have to turn there. I'll give you all the information you need. But we're looking at randomly sampling a woman age 40 or more. So women 40 years or more. And of those women, we know that 1% have breast cancer. And 99% do not. Now, here's an unfortunate truth about testing in medical situations. If you go for a medical test and it comes back positive, there's a possibility with any test that that's inaccurate. Or if you go for a test and it comes up negative, there's also a possibility that that's inaccurate as well. So if these women go for a mammogram test, which tests for breast cancer, 97% of the time, if a woman has breast cancer, the test will give a positive result, saying that, hey, we detect cancer. It detects cancer. But 3% of the time, oops, too many zeros there. 3% of the time we're going to get a negative result. This would be a false negative. So this woman has cancer, or a woman has cancer, but the test doesn't detect it. That's an unfortunate truth to the medical testing. Now, if you don't have cancer, there is also a possibility that the test will tell you you do. And if you don't have cancer, there's a better chance that the test will be accurate as a negative result. Right? So, which of these two, this would be a false positive, by the way, which of these two would be more serious in this situation? The false negative or the false positive? False negative, yeah. Because the woman goes in, takes the test, the doctor says, oh, we don't see any cancer, you're good. So she walks out going, yay, I'm good. When in fact, there's cancer there and it's growing, right? That could be very serious for this person. Definitely a serious situation. That's serious. This is a problem, however, because here, this woman goes in, takes the test comes back positive that you have breast cancer. So it's less serious because they're probably going to go through further testing, right? Here, this person's walking out thinking they're scot-free and probably not testing again. Does that make sense? So this one's probably going to get retested in some way or another. So this one's less serious. But it's still a problem. All right? Although this is not good news either, right? You've got cancer and we've detected cancer, but at least you know what you got. So what's the probability that a woman, 40 or more, has breast cancer and the cancer is detected by the test? So these would be independent events here. So I'm going to multiply 0.01, the probability that a woman at random has cancer, times the probability that the test is accurate and tells her that she has cancer. And so that's going to be 0.0097, which could translate pretty easily into 97 women out of 10,000 have cancer, and the test tells them accurately that they have cancer. Okay? This one's going to be 0.01 times 0.03, which is going to translate into 3 women in 10,000 are going to walk out of their doctor's office thinking that they're scot-free when they're not. That's an unfortunate reality of medicine. Okay. Here, we've got 99% of the women don't have cancer, but 6% of them are going to test positive for it even if they don't have it, which is 0.0594. So about 6% of them, or 594 out of 10,000, are going to think that they have cancer, at least for a little while, until they find out that they don't. Okay. That's pretty scary. This is terrifying. That's definitely terrifying. That's really scary. But you'd never know. And then 99 times 94 is going to give us the probability that a woman walks into her doctor's office, gets tested, and walks out without cancer, and the test is telling her the truth. So about 9,306 out of 10,000 are going to be in good shape. So, any concerns here? This is how a tree diagram works. And then you could actually ask other questions like, what's the probability that the test is negative? Well, that's going to be this plus this, right? What's the probability the test is positive? This and that. What's the probability of getting a false negative or a false positive? That's going to be the addition of your false negative and false positive, right? So there's lots of different ways you could ask questions or be asked questions based on this, but it's a really nice way to kind of make something visual that can make, I think, walking through the problem a little easier. I've actually had this conversation with my doctor. I now completely forget what it is that the test was for, and I can't remember if I was talking false negative or false positive. But if you've got a good doctor, he's looking at multiple things. He's not just looking at one test. He's looking at maybe some blood tests and possibly some other symptoms that you may have to kind of put together the answer that we're looking for on this. But it's why a second opinion is important whenever you're dealing with something that's serious or causing you pain. The other thing is, trust your gut. I mean, if you know something's wrong with your body, you know something's wrong with your body. And if some doctor says, hey, you're fine, go get a second opinion. I would say, for sure. Because not that everybody's going to deal with breast cancer. Men have similar issues with other bits and pieces. But anyway, that can happen. There's another one that I want to talk about. It's kind of an interesting problem. It's the Challenger disaster. It's on page 345. It's another example. I apologize for that. I actually was a high school junior when the Challenger exploded. If you've seen the video, it takes off, it gets a few miles up in the air, actually quite a ways up in the air, and then it explodes. Have you guys seen that footage at some point? Well, what caused that was the sections of the rocket booster are pieced together, and there's an O-ring, a rubber O-ring, that seals them together. They must bolt together as well. But one of the O-rings failed, and there was an engineer from the company that made the O-rings, Morton Thiokol, that basically did everything he could to try to stop the launch, but NASA decided to launch anyway. So here is the probability, given the temperature, because the temperature on that day was a problem. It was sub-freezing. There was ice on the launch pad, and I think, if I remember right, they had launched one other time with that low a temperature, or about that low a temperature, without a problem. So NASA said, "Oh, we're good." But the reality is that low temperature was an issue. So the probability of success for an O-ring was given as, in this temperature, as 0.977. So let me ask you this. If you knew that there was about a 2% chance of failure, and you were getting on the spaceship, would you get on the spaceship? You say no? Grace, what do you think? Would you get on the spaceship? 2%. I'd risk that. Just for the record, I'd risk that. Okay? Because there's no launch into space that's ever going to be 100% safe, right? There's always going to be a risk. And if 2% was the risk, 1 in 50, I'm going to die, I would take those odds. That's me, though, okay? Because I'd really like to see what it'd be like to be out in space and kind of float around. Okay, I have dreams, right? I don't think I'm going to realize those dreams, but hey, I have dreams. But this is for one O-ring. What's the probability that they're all successful? Each O-ring is its own entity. So that's an independent problem. So I'm going to take 0.977 and I'm going to multiply it times itself 6 times, because there are 6 O-rings. Now, 0.977 to the 6th power is only about 87%. So there's about an 87% chance that none of the O-rings fail. Now, you were at a no at 2%. You're definitely a no at 13%, right? Would anybody care to crawl on top of a spaceship if you knew that there was more than a 10% chance of failure and death? I got one. I got a couple of you. Okay. All right. The risk takers. That's a little bit like, forgive the example, but it's a little bit like taking a revolver with 7 bullets, a 7-shot revolver. I don't know if that exists. And putting 1 bullet in, spinning it, and then sticking it to your head. Would you do that? Okay, then you have a death wish.
Well, it depends on the amount of fun.
You don't even get to see space in that case, man. All you get to do is click. No, okay. You know, there's no chance of benefit in that, right? At least with the space, you got a chance of benefit. Would failure be an uncommon situation with this percent? No. Something that happens more than 10% of the time is a fairly common event. So for NASA to choose to launch under these circumstances, when the probability of failure would be 1 minus this 0.87, 13%, is crazy. Yeah, I don't know if you know this or not, but it was the first launch with a civilian, and the civilian was a woman named Krista McAuliffe. She was a school teacher, I think an elementary or middle school teacher, I forget. And obviously she didn't make it. A number of years later, Barbara Morgan went up, and she was actually the second choice when Krista McAuliffe was when her life was cut short. She ended up going up later, a number of years later. I don't know the year. Maybe you know. Did she go up a couple times? I knew she went up at least once. But she's from Idaho. I think McCall, if I'm not mistaken. Is she? You've met her. Yeah, I imagine a few of you may have known her. I mean, Idaho's not that small or that big a place, right? Yeah, I'm sure she's really nice. So it was an unfortunate deal. and NASA made a bad call launching under these conditions. The probability was far too high for disaster. Now we've lost 2 space shuttles, one for a totally different reason, but they've shut that down now. Okay, give those problems a try. Call me over if you have a question. I do need to pick up the tests. I had a quiz for you, but I think I'll save it for another time.